Good morning, students.
Good morning, sir.
All right, I welcome you all to the day 2 of the Physics in 5 days. These are the topics that we're going to be considering, and they are majorly under mechanics. So you'll discover that this one appeared yesterday, so it was shifted to today because we couldn't do it yesterday because we were pressed for time. So today we are going to be starting with it: density, relative density, and pressure. All right, let's go. Density. Just like we did it yesterday, we are going to be using the all-inclusive chemistry textbook for questions, and as well calculation in physics for questions. But of course, do well to engage. We are going to stick with the plan, a brief introduction, then questions. Is that okay? All right, so what is density? Density is defined as density is denoted by rho, and it is defined as the mass per unit volume of a body, right? Mass per unit volume of a body, and the SI unit is what? Kilograms per meter cube. Kilogram per meter cube. And we know that the density of water is about 1,000 kilogram per meter cube. However, when we solve, we are going to be given this constant. But just so you know, that's the density of water. Now, under density, the resistivity is not under here. Resistivity, the symbol for resistivity here is the same. Rho too, but that's under electricity, resistivity, conductivity. You get it? So they are inverse, right? Do you remember? All right. But this one is under mechanics. This guy is under electricity. So that's why we use, and there are some conventions like that that overlap. There are many conventions like that that overlap. The only ones that I think we don't use in mechanics at all is lambda, that we reserve for just waves and optics. All right. Okay, so the scientist that first studied density, we talked about him, was Archimedes, right? Archimedes. And he was the one that postulated the law of flotation, right? But first, he has one principle that is very common. Archimedes principle states that it says that when a body is wholly or partially immersed in water, are you listening to that? Let's just first understand that. It says when a body is totally, that is wholly, or partially, that is halfway or not totally, is that okay? Immersed in water, okay? Something like this. So we could have a system like this. We have water. This one is, what kind of immersion is this? Wholly or partial? Partial. Then if I have a system like this, what kind of immersion is this? Wholly. How about this one? Both are wholly. Is that okay? As far as the water covers it up, that is wholly immersed in water. Is that okay? His principle now says that for a body that is wholly or partially immersed in water, it always experiences an upthrust. So there's an upthrust, which is a force, upthrust. So it experiences an upthrust, which will be equal in magnitude to the weight of the water displaced. So he now says in his principle of flotation, that for a body to float on water or in a fluid, it has to displace its own weight. Does that make sense? So what this is basically saying is that if this system were to be an Eureka can, I said that it's Eureka can that we use for the experiment. The moment then we'll put another vessel here that can collect that guy. Maybe that vessel will now be sitting on the beam balance I'll use to measure the weight. So the moment you drop this body in here, this body here is going to displace its own weight. Does that make sense? So if it were inside water, it will displace the volume of water that it will displace will be equal to the volume of this body too. Do you understand now? Yes, and think of it is just simple because it is matter and it has mass and occupies space. So what it's just doing is taking the place of a particular fluid inside this case, right? So that is why the fluid that is taking the place will be displaced. Does that make sense? So that if you measure the weight of that guy and the weight of the substance is equal. Is that okay? That's what this principle states. Okay. So we said Archimedes' principle says that when a body is wholly or partially immersed in water, it experiences a force called what? Upthrust. Is that okay? So the upthrust is a force, so it's a vector, right? Right. The upthrust is represented by U. Now, it's experiencing an upthrust. So upthrust is an upward force, right? So now a very, very common, a locus classicus of this phenomenon is when you want to fetch water. If you throw a fetcher inside water, when do you feel the weight of the fetcher? You discover that if that fetcher were to be a heavy one that could really go into the water, sink into the water, if you are drawing it up, you want to take the office of someone. If you are drawing it up, are you listening to me? If you are drawing it up, you see that you will not feel weight much yet, right? Until it comes out of the water, then it now becomes heavy, right? Good. It's because that time when it was inside the water, something else is helping you to push it up, kind of. Is that okay? It's upthrust. So when it's inside water, it experiences what is called loss in weight. So upthrust is equal to what? Loss in weight of the body. Is that okay? Upthrust is also equal to the weight of water displaced or weight of liquid displaced. Does that make sense? Displaced. Okay. All right, so these two things hold. And the formula for upthrust, therefore, will be what? U sub any liquid will be the weight of the substance in the liquid minus weight of the substance in air, right?
No, sorry. Weight in air minus
Yeah. Weight in air minus weight in water, thank you, in liquid. So that will be weight in air, which will be heavier, right? Isn't it?
Yes, sir.
Okay, minus weight in liquid. We're only just starting now. All right, so that's upthrust. Is that clear? All right. So. There's now something called relative density. Another name for relative density is specific gravity. Another name for relative density is what?
Specific gravity.
Okay. So relative density is defined in different ways. So we are going to write like 1 million formulas. We have relative density for solids. We did all this, right? Relative density of solid. What will it be? It will be the mass of the solid over mass of equal volume of water, right? Then we also have that it could be the weight of the solid, if it can be mass of the solid. It can also be weight of the solid over weight of equal volume of water. Does that make sense? It could also be the weight of the solid over upthrust in water. Does that make sense? Now, how about relative density of liquids? What would that be? That would be the mass of solid in that liquid, right? In that liquid over the mass of the solid in water, right? Right? Like basically we can say that the primary equation for relative density is the weight of a substance in whatever I want to check over a reference substance. And our reference substance in this case is always what? Water. It's always what? Then we also have upthrust of object in that liquid. Upthrust of object. So no weight, no mass, sorry. This one is not correct. Is upthrust of the solid in the liquid over upthrust of the solid in water. Is that okay? The next one is also weight of object over upthrust of, we've done that. Then volume of liquid displaced by the object over volume, yes. Then that's another one for liquids. Volume of liquid displaced by object, volume of liquid displaced by object over volume of water displaced by the same object. Over what? Displaced by the same object. All right. So now that we have all of this, let's take some questions. Yeah, that is all we need to learn on relative density. The reason why students have problem with relative density and density is because it takes understanding. Is that okay? And these days students don't want to understand the concept. They don't want to apply formula and go. And he said yes. But is that okay? It's not so okay now. Okay, give me this. Give me this. Give me this. 40 meter cube. Are you writing? Or pause it, let me write on the bottom. There's another formula we'll be needing. You know, we said that upthrust in liquid is equal to the weight of water displaced. Right? Isn't it? Now, what is weight of water displaced? The weight of water displaced is the mass of water times acceleration due to gravity, right? Mass of water times acceleration due to gravity. And you know that water, the density of water is equal to mass, density of water is going to be mass of water over volume of water. Does that make sense? Okay, so then mass of water, therefore, will be equal to density times volume of water. Does that make sense? Okay, so if we substitute that into it, it means that upthrust in liquid will be equal to the density of the object this time times volume of liquid times acceleration due to gravity. Is that okay? So that's one more formula we should know. Let me verify that this thing should be in the beginning here. Density of the fluid, volume of, no, it is density of the fluid, density of the liquid times volume of the object. So, or volume of, equal volume of water. Yeah, volume of the water displaced. Does that make sense? So, density of the liquid, which is water in this case, times volume of water displaced. You know, the volume of water displaced is going to be the volume of the object. It displaces its own volume, right? Times G. So, basically, U is rho Vg. That's the point. So don't forget to, the density is the density of the liquid, the volume is the volume of the object, which is volume of water displaced. It's because of many things. One thing I mean more than one thing. One thing I mean like 2-3 things. That is why it confuses students. These calculations. Okay, let's apply the formulas we have learned. Are we done? Should I clean? Okay. Now the first question here says, now you can pause the video and attempt them yourself. We have 40 meter cube of liquid P is mixed with 60 meters cube of another liquid Q. Okay? In such a condition, what will be affected? If you mix liquids, which property will be affected physically? The volume, you know we are describing three things here now. Solution, we are describing three things here. We are describing density, we are describing mass, and volume, right? Which of these will be altered physically if you mix two liquids? The volume, yes, because it will increase, right? The mass too will be altered now physically. Don't you think so? The miscibility, the density will be dependent on the miscibility. Is that okay? Do you understand what I'm saying? All right. So that's why even in chemistry, we talk about concentration, which is actually density, isn't it? Mass over volume. You get what I'm saying? Okay. So the density is not a physical it will not be affected physically, right? But provided the liquids are miscible, the density will definitely be affected. So we have this guy, 40 centimeter cube of liquid B. So it means volume of liquid P, let's call it VP, is equal to what? 40 cm cube, right? It's mixed with 60 that of the other guy, VQ. That was 60 meter cube. Eh? Oh, sorry. Thank you. If the density of P and Q are this and this respectively, so density of this guy rho P is what? 1 kilogram per meter cube, and rho Q is 1.6 kilograms per meter cube. So what is the density of the mixture? Okay, so the resulting mixture, let's call it M. So the volume of the mixture first, let's get the mass of this guy. So M, mass of this guy, remember that, or recall that the density of this P guy will be equal to the mass of P over volume of P. Is this clear? Deborah, is this clear? Okay, so mass of P will now be equal to what? 1 times 40. So this is going to what? 40 kg. This is the mass of the liquid P. Then the rho of this guy, recall also that it is the mass of Q over the volume of Q. So that mass of Q is equal to what? This guy times this guy, right? Which is 60 times 1.6. That what? 96 kg. So the mass of the resulting mixture, that will be mass of Q plus P, will equal to what? 40 plus 96. That becomes 136 kg. So this is the mass of the resulting mixture. Then what will be the volume of the resulting mixture? The volume of the resulting mixture will be what? 100 cm cube, 100 meters cube. Does that make sense now? So what do we have here, therefore? We're looking for the density, right? Isn't it? It says, what's the density of the resulting mixture? So the density of the resulting mixture will be equal to the mass, which is 136 over the volume, 100. 1.36 kilograms per meter cube. Is this clear? Is it hard? No. All right. So will you attempt number 2? Okay, I should just go ahead. I should do my property.
Yes, sir. Yes, sir. Let us attend.
Some people have attempted. Is it hard? Should I just do it? There's another question like it here. I'm seeing one ratio here too. There's like 2 ratios. So you do the second ratio, right? That's the deal. Okay, let's do it together then. Should I wipe this? Okay, let me wipe this. So you must have copied all of these topics. So I'm going to wipe them. Okay, let's go. It says a solid weighs this amount in air. So weight in air is equal to, let's convert it to weight because this is in, okay, first, let's even convert to kilograms first. Is that okay? Let's convert to kilogram. But since everything is equal, the units are equal. You know it won't affect, you know? So we can solve with grams. Are you good with me? We can solve with grams. So the weight of that guy in air is 4.8 grams. And in water, weight of that guy in water is 2.8 grams. So what will be the upthrust of the body, upthrust in water of the body, or loss in weight of the body in water? It's what? 4.8 minus 2.8. That becomes what? 2. Okay. And 3.2 in kerosene. So weight in kerosene, the base of K will be what? 3.2. What will be its upthrust in kerosene? That will be 3.2 minus 2.8. What does that give you? No one. 0.6. Thank you. No, not 0.6. 0.4. Because 4 plus 8 is 12. Okay? Are we good? So it now says calculate the ratio of the density of solid, the ratio of the density of the solid to that of kerosene. Okay, to that of kerosene. To that of kerosene. The ratio of the density of the solid. Okay. The ratio of the density of the solid to that of kerosene. Okay, you know that relative density, yes?
This option to kerosene.
Mm.
How is it in the weight today?
Is the weight in air we use now? Oh, sorry. This guy minus this guy, oh, sorry. It's always weight in liquid and weight in air minus weight in liquid. Is that okay? So weight in air, 4.8 minus, what is weight in liquid? 3.2, 1.6, okay. So if we want to do the weight, the relative density of kerosene, relative density of the liquid, are you with me? What will it be? It will be the upthrust in liquid, which is 1.6, does that make sense? Over, let's write the formula. The relative density, are you with me? Of liquid is going to be the upthrust, please focus on the board now. Upthrust in liquid over upthrust in water. We wrote this formula, right? Okay. So the relative density of that liquid is going to be, what's the upthrust that guy experienced in that liquid? 1.6. What's the upthrust experienced in water? 2. This becomes 0.8. Okay. Okay. Then what's now the relative density of, okay, first, another thing is, I said relative density is also known as specific gravity, right? Then it doesn't have units. Is that okay? You discover now we have found two, or if you recall now rather, we have found two quantities that don't have units. Relative density and coefficient of friction. Do you remember? Okay. So RD of solid now will be the weight of water displaced over weight of equal volume of water, or weight of, which other formula can we use there to get the relative density of the solid now? That will be weight of the solid in air. What's the weight of the solid in air? 4.8 to the weight to over upthrust in water, right? What's the upthrust in water? 2. Does that make sense? So this becomes what? 2.4. So then the ratio of the density of the solid to that of kerosene will now be the ratio of the solid to that of kerosene will now be, what's the density, relative density of kerosene? 0.8. Solid is first 2.4 over, that's ratio, right? Yeah, we can use it to represent density. This is the relative density of the liquid. Is that okay? So we're using it to represent the density. You understand what I'm saying? And more like, it's not exactly the same. Is that okay? Only that this is going to be the ratio too of the densities. If their relative densities are this, does that make sense? If the relative density of this guy is 0.8 and the relative density of this guy is 2.4, the ratio of those two relative densities will be the ratio of their densities if we add their densities. Does that make sense? So this will become 1, that's 1 right here, right? 3 here. So that's about 3:1. That's the answer. Right. Are we good with that? Is it clear? Okay. Let's go to number 3. Will you try number 3 for me? Or I should do it. Okay, try it then. Please pause it. It says an empty relative density bottle has a mass of this. So the mass of the bottle is 20 grams. When it is filled with, that's when it is filled with petrol. Okay, no, when it is empty, it's 20 grams. Then when it is now filled with petrol, it has a mass of, so that is now mass of bottle plus mass of petrol is now what? 55 grams. Okay, so since mass of bottle is 20 grams, so 20 grams plus mass of petrol is what? 55 grams. This makes sense, yeah? So the mass of petrol will therefore be what? 55 minus 20 is equal to what? 35 grams. That will be the mass of petrol alone. It now says calculate the mass of the bottle when it is filled with water. First, what you want to get is the mass of water. The mass of water. So you use a formula that combines them. Am I clear? So relative density, so I'm already given the relative density of petrol, right? To be 0.7. So relative density of liquid, right? Of liquid now is going to be the mass of liquid over the mass, our reference is water, the mass of equal volume of water. Is it clear what I did? So I'm taking the relative density of the liquid because that's what we are given, mass of petrol, relative density of petrol. So that will be the mass of liquid over mass of equal volume of water. It's always weight of that substance over weight of equal volume of water. Equal volume because we are filling the bottle up to with water. So it's the same. So the mass that will occupy the same volume of water, the same volume as petrol did inside that bottle. So relative density is now what? 0.7 is equal to the mass of the liquid. So what's the mass of the liquid? 35 over the mass of equal volume of water, which is x, I don't have. So that becomes x equals 35 over 0.7. You move this 357 here, 50. So x is equal to what? 50 grams. Now this is now the mass of equal volume of water, mass of water. It now says calculate the mass of bottle when it is filled with water. So we now say mass of water now plus mass of bottle will be equal to what? 20 plus 50, that's 70. Is it clear now? Will you try number 4? Have you got number 4? Yes? 0.4, okay. That's good. I don't know if it's correct though. Where did I pick this from? I'm going to use the heuristic approach. A block of material of volume this. So volume of block is, now watch, oh please, watch. But there's no simpler way of breaking something that is already simple down. I don't know. A block of material of volume this. So the volume of block is 2 times 10 to the minus 5 meters cube. And density this. Density of block is already, and density this. 2.5 times 10 to the power 3 kilograms per meter cube. Here, find the mass of the block first. So the mass of the block is going to what? The volume of the block times this, right? Since density is mass over volume, so mass equals density times volume, okay? So here we can say that 2 times 2.5 times 10 to the power minus 5 times 10 to the power 3. This becomes 5 times 10 to the power minus 2 kilograms. That's the mass. But we need weight because it's weight that the spring balance will measure, right? So we can easily just say the weight of block either way is 5 times 10 to the power. You know, weight is equal to mg, right? Okay, so weight of block therefore will equal to this mass 5 times 10 to the power minus 2 times 10. You do this by 1, so it becomes weight of block equal to 5 times 10 to the power minus 1, or 0.5 Newton. Okay, this is what you said you got. And you stopped there. Was it weight you were looking for? No. Okay. No, it still says is suspended from a spring balance with half of the volume of the block immersed in water. Half of the volume of the block is what? Is immersed in water. Okay. So let's go and say that half of the volume. So the volume that is immersed in water is going to be half the volume of the block. Now what is half the volume of the block? 1 over 2 times 2 times 2. This guy times 10 to the power minus 5. So the volume immersed in water now, are you with me? The volume immersed in water is going to be 1 times 10 to the power minus 5 meters cube. Okay, so volume of block immersed in water. If it is the volume of immersed in water, this volume will be the volume of water what? Displaced. Does that make sense? It will displace its own volume or displace its own weight in water exactly. Okay, so what now happened? So now 1 times 10 to the power minus 5 meters cube. Is this one clear first? Is this portion clear?
Yes, sir.
Are you sure?
Yes, sir.
Deborah. Is it clear? See who I'm talking to? Yes. Are you sure? Okay, because you come to the board and redo it, I will claim it. Okay, he said okay. All right, let me go again. You know how we did here to get the mass and the weight of this thing, right? We have not even used it. So it now says that half of the volume of the block is immersed. So let's take half of the volume that is immersed. So that half of the volume that is immersed is going to be the volume of water that will be displaced, because a body displaces its own weight in water. Okay, so this is the mass volume of water that will be displaced. Okay, it now says what is the reading on the spring balance? Okay, now what do you think will be the reading on the spring balance? The reading on the spring balance is going to be the upthrust in water minus the actual weight of the body in air. Does that make sense? So what are we looking for? We have found the weight of the body, right? So we have to find the upthrust in water or loss in weight in water. If you're not clear on that, raise your hand. You're not clear? You're clear? You're not clear on that? Is it what the reading on the spring balance will be that you don't understand? What will the water, the spring balance read? It will read the apparent weight, which is the false weight. Does that make sense? Apparent weight is the weight that is not true, that the body has inside water, right? That's what the body we have, which is equal to the weight in water. You remember that we said upthrust is equal to weight in air minus weight in water, right? So it means that weight in water is actually weight in air minus upthrust. Does this make sense? And so let's first find the upthrust of that body in water. That's what we're calculating. And recall that upthrust in that water is going to be the weight the loss weight of water displaced, or weight of water or loss in weight. Does that make sense? Anyone that we use, do you understand? If it's loss in weight, then we know it's upthrust. If it's volume, we're not using volume, I'm using weight now. Loss in weight or weight of water displaced. Does that make sense now? Because the weight of water displaced is the weight loss for the body inside water. Is it clear? If you are not clear on that, raise your hand. Are you sure? Okay. The weight of the weight that the body loses in water is going to be the weight of the water that it displaces. All right. So basically, what we want to find is the weight of the water that it displaces. The weight of water displaced. Okay. So very easily, this is very simple now. Since we have found the volume of water displaced, what is the density of water? Okay, are we giving? Yes, I even give you density of water. So what's the density of water? That will be 1 times 10 to the power 3 kilograms per meter cube. What is the volume of water displaced? The volume of water displaced is going to be what? 1 times 10 to the power minus 5 meters cube. Does this make sense? So it means that the mass of water is going to be the density of water times the volume of water displaced. Does that make sense? So the mass of water that is displaced is going to be the density of water, which is 1,000 basically, please, times 1 times 10 to the power minus 5. Okay, I see why they are using that. So that becomes mass of water is going to be 1 times 10 to the power minus 2 kilograms. That's okay. So it now says, what is the reading? Okay, so this one is the mass of the water displaced. So what is now the weight of the water displaced? That will be the mass of water displaced times acceleration due to gravity, right? That's 1 times 10 to the power minus 2 times 10. Does this make sense? That will be 10 to the power minus 1, which is what? 0.1 Newton. So it means that the actual weight of the guy in water is now its weight in air. Is it now clear? So minus the upthrust, that will be its weight in water. If you're not still clear, John. Okay. I found a simpler way to explain it. Who has not understood yet?
Is this not weight in water?
It's confusing. Is it confusing you? A simpler one. A similar question. Okay, a simpler one. Okay, you want me to solve a simpler question again? No, I will write another set of questions. Let me reiterate. First, let's solve this, and I'm going to show you. I'm going to re-explain it. Weight in water. Now, what's the weight in air of that guy? 0.5 minus the upthrust he experiences now what? 0.1, which is what? 0.4 Newton. Okay, now let's cover this. This is our answer now. Let's go again. It says, if you are sleeping now, what's it? Now listen, it's very simple. It says a block of material, or should I clean it and resolve? Maybe that could make it clear. a block of material of this volume. This is the volume of the block. This is the density of the block, right? As given here, is suspended from a spring balance. Okay, sometimes I forgot to mention this also. Whenever you are given a question in physics, try to draw diagrams. Is that okay? So we have a spring balance, and a block is hanging. Let's draw a block that looks like a square. A block of material is hanging halfway, so only half of its volume is immersed. Are you with me now? So this, listen now. So let's say it was a Eureka can. Are you with me? Please watch. Just you are going to get it now. If it was a Eureka can, if it were a Eureka can, some of this water would have spilled here, isn't it? Right? Yes, sir. Okay. So first, having the density of the body and the volume of the body, let's calculate the mass of the body. So we have the mass of the body is going to be the volume times the density of the body. So this is the mass of the body. What is now the weight of the body in air? Weight is mass times acceleration due to gravity. Does that make sense? So we did this and we got this. Okay. Now it now says that it is suspended from a spring balance with half of the volume of the block immersed in water. If half of the volume of the block is immersed in water, it means that the volume of water that will be here will be equal to what? The weight of the body. That is the weight of the, or weight. If half of the volume of this guy is immersed in water, it means that the volume here is also what? Half. Do you get it now? So now let's now calculate the properties of this guy. We have known the volume of this guy because it is half of the volume of this guy. Does that make sense? It has displaced some water, which will be equal to the volume of this guy, the volume that is immersed in water. And we know now that it is half its volume that is immersed in water. So it means that this volume of water that is here is half the volume of the body. Okay, we calculated that half volume to be this guy. So the volume of water displaced is actually this guy. So what is now the density of the water? We know density of water, right? Is always this, right? So what is now the mass of this water that is displaced? Is it clear? The mass of this water displaced is going to be the density of water times the volume of water displaced. Is this clear? So we got that mass of water to be this. So when we now find the weight of that water. The weight of that water will be this times 10. It gave us 0.1. And we know that this weight, the weight of this water, is equal to the upthrust felt by this body. Isn't it? Okay. So in answer, you should find the reading on the spring balance, which will be the weight of that body inside water. Right? And we know that the weight in water is the weight in air minus the upthrust or loss in weight that is experienced, right? So the loss in weight is experienced is what? 0.1 Newton, because that's the amount of, think of it as the amount of weight that was lost. Does that make sense now? So by the time you now subtract the loss in weight from the actual weight, you're going to get the weight in water. Is it clear? You sure it's clear? Okay. Yes, dear. Number 5, yes. 0.8. Okay.
Yes.
You solved it too. Okay, good. Do I need to solve it? Okay, pause it. Let me clean the board. Huh? Bottle rather. A mass of specific gravity bottle, 15 grams. So the mass of the bottle is what? 15.2 grams. More like your minds are not even here. Are you listening at all? It is this when filled with kerosene. So the mass of the bottle when filled with kerosene. So this is now the mass of bottle plus mass of kerosene is what? 24.8 grams. So what will now be the mass of kerosene? That will become 24.8 minus 15.2 grams. So the mass of kerosene will have what? 9.6 grams. If you have solved it to this point, raise your hand. Okay. So it now says, and 27.2 when filled with distilled water. So mass of bottle plus mass of distilled water. Let's just use water. So is 27.2 grams, it says. So what will now be the mass of water? That what? 27.2 minus 15.2. So mass of water will be what? 12. Yes, exactly 12. Good. Exactly 12 grams. So this is the mass of water. And they have equal volume because they are filling the same bottle. So calculate the relative density of kerosene. Relative density of kerosene will now be what? Mass of kerosene over mass of equal volume of water. You got it right? And so what did you not say you don't understand about this? It's simple now. Do you understand it? Come and solve this lesson for us. You have been sleeping. Sit. Yeah, possibly. Now, what is pressure? Pressure is defined as the force exerted per unit area. Force is defined, pressure is defined as what? Force exerted per unit area. So, yes, per unit area. So, what that is saying is that, for example, now, if I apply pressure with my palm, are you listening to me? On this surface, if I apply pressure on this surface, when will the pressure be higher? Is it when I apply this force with my hand open like this, or I put my hand like this and I apply pressure? When will the force felt per unit of the area I'm applying it on, when will it be higher? When will the pressure be higher, or when will the force? No, when will the pressure be higher? Provided I'm using the same force to push on this board. Is it when I'm doing it like this, or when I'm doing it like this? When will it be higher? Because some people think it's like this, others think it's like this. Okay, wait. So wait, calm down. Let's get it. So which of these have the higher area? Is it this or this? These have a higher area, right? So this one has a smaller area, right? If you divide by a big number, what will you get? Will you get a big number, or if you divide by a small number? When will you get a big number? Is it when you divide by a small number or you divide by a big number? Okay, everybody agree on that. So it means that is when the area is small that the pressure is what? Higher. Does that make sense? We've talked about it. They are inversely proportional. Is that okay? So pressure on this surface is going to be higher when I impress this on it than when I impress my full hand on. Is that okay? So a woman that is putting on stiletto, and you don't know stiletto, you know what I'm going to do, right?
Yes, sir.
The pressure we will apply on the ground will be different from will be more than when someone that is putting on something like this. Is that okay?
Yes, sir.
Because this one has a tinier surface. You know, there are some stilettos that are actually they are thin kind of in the edge. So because their weight is their force. Is that okay? Is the force we are considering in that case. So their weight is still pushing on the ground. So the surface, the force, the pressure that will be felt in that surface, or the force rather, that will be felt in that surface will be greater than when you put on slippers. Do you understand what I'm saying? The reason is this: the higher the surface area, the more dispersed your force is. The more spread your force is. That okay? That is why if you lie down, there's a question in JAM that asks about when will the pressure that, or when will the person sink also? Is it when the person is lying down on the beach? Have you seen that question before? That when the person is, if the person lies down and the person stands, when is the person likely to sink more? More likely to sink? Stand, because he's impressing more force or more of his weight in a surface, is that on a surface rather? Unlike when he's lying down. When he's lying down, his whole weight is spread abroad. Does that make sense? All right. Now let's talk about, yes? So let's talk about pressure in fluids. See, it's simple. It's just there's one thing that came to my mind as you. Okay. Have you seen ants carrying? Okay, there was one movie I saw. A group of ants, they were carrying water. Is that okay? They were carrying water with leaf. Is that okay? So as they were going, when everybody held it at different parts, they were moving, and they weren't moving fast, they were moving slow and crawling. So the ones that were now under, they were now like, they were tired. While they were crawling, and the ones in front were walking. Is that okay? That they too should stand and, So what happened was the ants now left that thing, then the water now poured to the ground. So my question is now, did the weight of the water increase all of a sudden? Those guys, as they were leaving, they were still holding it. But the water poured because the unit area where the force is concentrated, where the weight is concentrated, is now smaller. Do you understand now? Yes. So that's the pressure thing. So the person will sink when he stands more than when he lies down. Do you get it? All right. Okay. We said that this man did what? Okay, pressure in fluids. All right. With pressure in fluids, we consider two major cases. But the first thing is, let's talk about the properties of pressure in fluid. One is the fact that it is, with depth of the fluid, with the depth of the liquid, the pressure does what? Increases. Do you know that? So pressure increases with the depth of fluid. Pressure in fluid, it increases. So it means that a fluid at this point, we experience more pressure than fluid at this point. Does that make sense? Why do you think so? Because there is more weight impressing on this guy, right? Than there is the quantity of water that is pushing on this level is not as much as the one that is pushing on this level. Do you get it now? It's clear, right? Yes, okay. Another proven theory is, if you create a hole here, you create a hole here, and you create a hole here, where will this thing? Which of this is likely? That this thing is oozing out like this here, and it's oozing out just a little here, or oozing out like this here, and oozing out like this here. So this is these two, case A. This two, case B. Case A is the likely condition. Good. That's the answer. Because if you have ever done it before, you see that this one is going to flow faster than this. You understand? In fact, the moment this water gets here, this thing will start receding until it stops. If there's another hose here, that one too will still be more moving fast until this thing gets closer and closer to it. The water level will start receding, and like that, or the flow rate rather will start receding. So you're correct. So that shows that there's pressure here than at this point, right? So pressure increases with the depth of the liquid. Another thing is that pressure at the same point in a liquid is equal. Pressure at a point in a liquid is distributed equally in all directions. Pressure at a point. So let's pick a point in this liquid now. So we pick this point in this liquid, pressure at this point throughout this liquid is distributed equally in all directions around the liquid. Does that make sense? At this point, but it will be less than the pressure that is here. Do you get it now? So still alluding to the fact that it is increasing downward, but at the same level. Pressure, water at the same level, or liquid at the same level, we experience the same pressure in a tube. Does that make sense? All right. And that's going to help us to understand the concept of this concept I'm going to bring up now. In the YouTube, first let's bring about resolve pressure in liquids. So pressure in liquids given by the formula H rho G. How do we get it? We can say that since pressure is equal to force over area, we know that force is also weight, right? So since force is weight, and weight is mg over a, right? So pressure is going to be mass. You recall that mass is rho g. Do you remember that? Okay. No, it's not rho g, rho v rather. Do you remember? Rho v now. Let's see. That we just did. So since mass is that, we can say rho vg over a. Okay. So that pressure therefore becomes V. Volume is area times height. Do you remember? Do you know? Length times breadth times height. Since area is length times breadth. The reason why I introduce area here is because so that I can cancel out this guy. Okay. Times rho times G all over A. So this takes care of this, and pressure becomes what? H rho G. Do you understand? All right, now. This is actually only true when the body, now listen, when the tube in which the fluid is not open to the atmosphere, this is what you see, the pressure throughout the entire system. When it is not open, see, look at this tube now. I'm going to create a YouTube soon. But look at this guy now. The pressure at this point here now, if I close this thing with a lid, the pressure throughout is going to what? H rho G. But if I open it, is that okay? Atmospheric pressure will begin to act on it. Do you understand now? So the pressure in this fluid is going to be atmospheric pressure at any point here plus H rho G. Does this make sense? Is it clear? Are you sure?
Yes.
All right. All right. All right. Do you want to see me? Once you see that there is space here, this space is the space for atmospheric pressure to act. Does that make sense? So, and if you ask a question, I think there was one question in JAM too. They ask theoretical questions a lot here too about how that a person is able to drink drink water, drink with straw. Yes, because of atmospheric pressure. Do you understand? Yeah, so what happens is this. The moment the person fills the straw with water by suction pressure, there are two pressures there. There is suction pressure and atmospheric pressure. So the moment the person fills the water with suction pressure, fills the straw with suction pressure, atmospheric pressure will now push on the water and allow the water to begin to move. You'll now be taking the place of the one you are sucking. Do you understand now? So that's how the person is able to drink. What if you... you see, this is the idea. This is the idea. See, this is the idea. Even if you close it, as far as the water is not filled to the brim, the only condition I said is when the water is filled to the brim. Do you understand? If the water is filled to the brim here, H rho G. But if it's not filled to the brim, as far as there is air here, do you get it now? Even if there was no air here, there before, air, by the time you suck small, air has found its way inside because there is a space. You get what I'm saying? All right. In fact, by introducing the straw, if there was no air at all, by introducing the straw inside it, there's space inside. Do you understand now? So it has to take a space. The liquid will take some space, air will take another space inside it. Does that make sense? So that's why you're able to draw. So atmospheric pressure will now assist in. You get what I'm saying now? All right. Okay, so what if it was a YouTube system? YouTube. You beat who? Are you with me?
Yes, sir.
Pause it. Okay, so in this system, the idea is the same. The idea is the same. So the pressure at the same point on the tube. As far as the U-tube is regular, my own is not so regular. But if it's regular, the pressure at the same point will be what? Equal. So if I call this point A and I call this point B, the pressure here is equal to the pressure here. Does that make sense? Okay. Now, how do we get the pressure at point A? The pressure at point A is going to be the atmospheric pressure that we act here, right? Atmospheric pressure plus the pressure at this point. What's the pressure at this point? This point has a height h, right? Let's call this one h1. Let's say the water here is filled, or the liquid is filled to this point here. So, and this one has height of h2. Does this make sense? H sub 2. So that the pressure at point A is equal to what? H1 rho G. Does that make sense? H1 rho G. And because we are using the same liquid, the same fluid, the density will be the same. Is that okay? Now watch. The density will be the same. So pressure at point B will be what? Atmospheric pressure 2, right? Plus H2 rho G. Is this clear? Okay, stop writing now. So if it's the same fluid, pressure in the fluid must be what? Pressure at the same point in the fluid must be what? Equal. So it means that pressure A, PA must be equal to PB. So definitely we have A plus H1 rho G equal to A plus H2 rho G. If I subtract A from both sides, A goes away, right? So we now have divide through by rho. Does that make sense? So, okay, because it's the same fluid, because it's the same fluid, are you with me?
Yes, sir.
Acceleration due to gravity also cancel acceleration due to gravity. So H1 will be equal to what? H2. Okay, but I was looking for a condition where we'll get the Hertz, there's something called the Hertz apparatus. So look at the condition now. Where this fluid is different. Let's say this one now was petrol. Are you with me? Yes. Petrol is filled to this point B. So from this point B here, we have equal fluid, the same fluid. Are you with me? Yes. Okay. And this point A, so everything here, let's say this was water, H2O. So everything here is H2O to this point. Everything here is petrol. Does that make sense? So that the densities will be different. Density is not supposed to cancel out. Are you with me? Are you with me at all?
Yes,
okay. So in that kind of scenario, we see that pressure at point A we got what? Atmospheric pressure plus what? H1 rho G. Are you with me? Just get it. Just follow me. The pressure at rho 1. Thank you. Because the liquid here is water here, H2O here, throughout to point B. Are you with me? Of course, we use something to block it, so that's what I mean. You get what I'm saying? Okay? That's the way we determine pressure of other fluids. The barometric system. Barometric technique. That's what we call it. Is that okay? All right. What did I not say? A will now, pressure in B at point B will now be equal to what? A atmospheric pressure plus H2 rho 2G. This makes sense here? Yeah? Because they are equal, they are in the same level of the fluid, what will happen? Pressure at A will be equal to pressure at B. So that A plus H1 rho 1G is equal to A plus H2 rho 2G. This makes sense, right? If we subtract it from both sides, we have H1 rho 1G is equal to H2 rho 2G. This makes sense, right? G takes care of G. So we now have what? H1 divided both sides by H2 over H2 is equal to, divided both sides by rho 1, rho 2 over rho 1. Does this make sense? So this is another formula for that you can use in calculating pressure. I mean, this one is for density, and height in the... If you are confused, raise your hand. Nobody, right? Okay, let's solve like the questions you always find they are simple questions. So just master this one. H1 over H2 or H1 row 1 is equal to H2 row 2. H1 row 1 is equal to H2 row 2. That's what we have here now. Okay. So let's solve a question here. The questions are always simple. That's one truth. Yeah, of course. Shouldn't be asking me. A hatch door has an area 0.5 meters squared. The specific gravity of seawater 1.03. Assume that G, okay, you've been given all what you need here now, 2/2 squared, and neglect atmospheric pressure. What is the force exerted? What's the force exerted by the seawater on the hatch door? Force is what we're looking for. Remember that force is equal to, pressure is equal to force over area, right? Okay, at a depth, H is 200 meters. So first, let's find the pressure. Pressure is going to be what? H rho G. So if that's the case, then the pressure there is going to be what? H, which is 200, times 1.03 times 10. So pressure is going to 2060. Are you sure? Yes. Okay. So pressure will now be equal to force over area. And force is already giving us, force is what we're looking for. So we have gotten pressure to be this. So that force will be equal to 2060 times area, which is 0.5, that's half. That's 1030 Newton. Is it hard? Let's go to the next question. Next topic. What's the next topic, please? There are other questions. I'll send you. I'll send most of the questions are just apply the formulas directly. Is that okay? For most of the questions. All right. Let's begin with work. What is work? Work done is given by what? Force that is exerted over a given distance. Does that make sense? Work that is done on the body, force that is exerted over a given distance. So, for example, the work done on a body, the work done on a body to move that body over a particular distance is going to be the product of the force and this time net force, because provided the body we have weight that needs to be overcome. Is that okay? Net force times distance. So that if net force is MA times distance, what do we have? MAD. So we usually say work done is mad. Somebody say work done is mad. Do you have to do like this? All right, now let's go to energy. Okay, so basically, the other thing you could be told to do is this: that a body is on this surface, horizontal surface like this. Are you with me? And a force of, say, F Newton is acting on it at an angle 30 grandnaughts. Is that okay? You always resolve the force in the horizontal direction. If you are asked to say, find the work done by the force in this direction. Is that okay? Of course, you might be pushing also. Is that okay? So, but you always resolve to the horizontal direction so that F will become what? Work done will become what? Force times F cos theta times distance. Does this make sense for us? Okay. Okay, I'm supposed to use theta here. So that W equal to what? FD cos theta. This makes sense here? Okay. How do you resolve? Resolve this in horizontal direction first. Let me see you. You close the angle, right? And so when you are closing angle, that's what? Cos. Can we use cos or sine? You get what I'm trying to say, right? You're always resolving it in horizontal direction. Is that okay? The work you have to do on this body now to To do sine, it means you want to pull it up. So that's my point. All right, let's go to energy. So usually they ask more question on conservation of energy. What is it? Okay, so energy, let's go. Energy can be defined as what? What is energy, everybody? All right. Energy is the capacity to do work. And energy is divided into two. We have potential energy and what? Kinetic energy. So potential energy is the energy a body has by virtue of its position above the ground, the ground level, right? Is that okay? Or its position under gravitation. Is that okay? Gravitational force. Then kinetic energy is going to be the force. So we say basically potential energy is the energy that a body at rest possesses. Do you understand now? So a bulb hanging on the ceiling possesses what kind of energy? Potential. Is that okay? All right. Now a body that is moving possesses what is called kinetic energy. So we say kinetic energy is the energy of a moving body. All right. Now, so we said potential energy is given by mgh. That is the weight of the body times its height above the ground. Times what? Its height above the ground. Okay. While the kinetic energy of a body is given by half mv squared. Now, where you will be tested mostly is where there is conversion of energy. So look at this condition. Where this body now is, say this is Martins, he wants to push this body down the hill. He wants to push it down the hill. He wants to push it down the hill. All right, this monkey, Martins, okay. This monkey, no. This monkey wants to push this guy down the hill. Are you there? And here is not hill. This is a cliff. This is what? Okay. Now, this body here, before it gets pushed, possesses what kind of energy? First, is it moving? No. Is it moving at this point? No, sir. So if it's not moving, it means it possesses what? So all the energy it possesses is potential energy. The moment it gets released from here, energy conversion begins to take place. But total energy is conserved. Law of conservation of energy applies. Is that okay? Total energy is always conserved. Albeit there might be conversion from kinetic to what? Potential, or potential to kinetic, which will be the case here. So let's say the total potential energy here was 500 joules at the beginning of this journey before being pushed. And of course, when we say potential, what does potential mean? Capacity, right? Ability, right? What potential does it have here? The potential to do what? To fall. Do you understand now? That's why we call voltage to potential difference. Do you understand? The potential for electron to flow. Do you understand why? Because it is high on one end and it is low on the other end, right? So to flow from that high end to the lower end. Are you with me? So now, what will happen here is this. As this guy begins to fall, he begins to go down and go down and go down and go down and go down until it gets to here, which is just before it touches the ground. Is that okay? I cannot exactly estimate it, but it is always just before it touches the ground. Assuming that it has not touched the ground. Now here's what happens. Thank you. Energy conversion now begins to happen. By the time it gets here, it has lost some potential energy, especially because of what? Its height. It is height at this point that has done what? Reduced. Is it clear now? So because the height has reduced, the mass did not change. Assume the gravity is still 10, but the height has reduced, so because of that, it has lost some potential energy. So the potential, this thing might now be here around 450. Potential energy might be 450 here, and K will be what? 50 joules. Oh, sorry, I didn't talk about that. The unit of work done is what? Joules. Work done and energy, their unit is the same. Joules, named after James Prescott Jones, everybody.
James Prescott Jones.
James Prescott Jones.
James Prescott Jones.
No, don't mind. Some people cannot read English. All right, are you with me? So we have, we are online. We are online, right? Potential. Okay, so we said that PE is what 450 at this point. Midway through the journey, maybe we have like 200, 250 PE and what 250 KE, but total energy is still what 500. Actually, the conversion of energy is not perfect. Is that okay? In real life, the energy might be lost due to many things. Maybe as sound, as heat. You understand? So it's not always perfect, but in an ideal case, this is what we should have. Then by the time we get to height 0, just before it hits the ground, are you with me? That is, if we do the derivative of the most minute height, the smallest of height, right? P will be what? 0. And total energy will now be what? Only kinetic, which is what? 500 joules. Okay, so this is just the idea. So you will now see questions on where P is equal to KE, all those things. So where P is equal to KE, around here, P is equal to KE. We can calculate that. So where would the velocity be maximum? Just before it touches the ground. All right. Is it clear first? You don't know. Is when this body, when I throw it up, what happened is that it stopped momentarily as it got up and began to fall again. So what happens is that the velocity is reducing, and then as it's coming down, the velocity is maximum at the point just before it touches my hand back. Is that okay? So the same way here, that guy is maximum. So where P equal to ME, we have that MGH is equal to half MV squared. We just want to bring in some things. So for example, the mass is the same, right? So what will be the velocity at that point? V squared equal to what? 2GH. Does this make sense? So V equal to square root of what? 2GH. So the velocity at the point where P equal to K is what? The square root of root 2GH. Anyways, now let's talk about power. Now what is power? Power is defined as the time rate of work done. So we say it's work done over time. It is applicable to both mechanics and electricity. So, but it's just that in mechanics, work done is not just force times distance. It is what? What's the formula for work done in electricity? Do you remember? We said that work done is what? V over Q or QV, because V is the work done per unit charge. So QV, do you remember? So you can now begin to work some things. Just bring in things. Since work done is this, power in electricity will have what? Work done over time, which is QV over T. And power is equal to, recall that this one is IT, current times time times V over T. So what is power? IV. Do you see that? Like we could come up with many things there. Okay, so the unit of power is watt. The unit of power is what? And all of these three are what? What kind of, are they vectors or scalars?
Yeah, scalars.
God bless you. Scalars. Do you remember our this in mnemonic of yesterday? Is what? DMFM Vem what? Okay. So that for people that were not here, so let's quickly remind them. What is this? Okay, T squared. Thank you. So what is this guy? Displacement. This guy. This guy. This guy. This guy. This guy. Electric field intensity. Electric field potential or strength. Thank you. Electric field potential will be scalar. Electric field intensity is vector. All right. This guy. This guy. Weight, not work done. Okay, this guy, this guy, trust and tension. Good. Please, just remember how to resolve. Please learn that Lamister well. Oh. That you said you prefer that one that you turn into triangular law vectors. It's not everything we can change, right? Okay, so it means that Lamister and work in some, you use triangular law vectors for the others. All right. So should we? Okay, so let's solve just one question here. I promise you, all the questions are simple here. Is that okay? Oh no, let me just write the 2 questions or 3 questions you will solve. You solve everything, then. So it says if a ball has a mass of this and falls a distance of this, so the mass, use the heuristic method, 0.5, write your parameters. Falls this distance is 20 meters to the ground. And to the ground, what will be the potential energy? Since G is 10 meters per second squared, first, what will be the potential energy? It's going to be what? 20 times 10 times 0.5. This one gives us 5. 5 times this, 100 joules. So it means potential energy is going to be what? 100 joules. So this whole thing will be converted to kinetic energy. So since potential is converted to kinetic energy, then it means that P will be 100 joules equal to what? Half mv squared. So 100 joules equals m, which is 0.5 times v squared over 2. 200 by the time you cross multiply, right? 200 is equal to 0.5 times v squared. So what do we have? Divide both sides by 0.5 by 0.5. That will be 400 years, 1 over 2. V squared equals, divide this, 400, right? Square root of this. This is just direct self. V equals 20 meters per second, yes? It now says, and rebounds to a height of 6 meters. Calculate the velocity of the ball. So the velocity of the ball, what will happen to the, is after it rebounds that it has lost energy due to collision. If it did not lose any energy, by the time it touches the ground, how much height should it flow to again? Fly to 20 again, 20 meters. But the reason why it flew to only 6 meters is because it has lost some energy. So let's calculate the energy loss. So it's going to be P again equals mgh. So this time the same mass, 0.5, the same acceleration to gravity, but now the height is 6 meters. So the potential energy it had at that time is going to be what? 0.55530. 30 joules. So this is the amount of energy that is used to fly. Is that okay? So what will now be the loss of energy? Loss in energy will now be 100 joules minus the 30 joules that we lost, energy loss. It's going to be this as 70 joules. So it had lost 70 joules of energy by the time it hits the ground. Maybe due to heat, due to sound, due to many things that causes loss in energy. Is that okay? That's why I said the system is not perfect in real life. You get it? All right. So let's examine machines. Okay. So I'm not solving this. Solve the question. Put the answer in the comment section below. 10,000. Yes. 10,000 naira. What? There's another unit for power. It's called horsepower. Do you know what that is? 1 horsepower is about 736 watts. I can't remember, so verify. But you'll be given. If you need to put it in horsepower. Is that okay? Okay. Okay, let's go to machine. So what is a machine? A machine is a device.
A machine device
that uses energy to overcome
to overcome a higher by applying
whatever. The simple definition of machine. How many of you have seen Three Idiots? Three Idiots, the Indian movie. Eh, what did you define machine? A device that is used to make to help us do work or to help make work easier and faster to do. Do you get it? Yes, that's what a machine is. That's what a machine is. It uses energy to overcome a load. Does that make sense? Or to perform tasks, basically. Is that okay? Machines simply make work easier and faster, right? Now, there are some terms that we use to define machines. There are some terms we use to define machines. And they are, number one, the mechanical advantage. Is that okay? Now, mechanical advantage of machine is the ratio of the load that is used to overcome over what? The mechanical, over what? The effort that is applied. Is that okay? So basically, are you with me? Now, it's only mechanical advantage if load, if your MA, for example, now if MA is greater than, for it to be mechanical advantage, MA must be greater than, is that okay? If MA was less than 1, what will it become? Mechanical disadvantage. Is that okay? If MA is greater than 1, it's a mechanical advantage. But if MA is less than 1, it's a mechanical what? Disadvantage. Are you with me now? Okay. So, and when will MA be greater than 1? Only when the load is greater than the what? Of course, because that's what a machine does. It uses small effort to achieve a particular larger task. Do you understand me? All right. Now, there's another term known as the velocity ratio. The velocity ratio. Velocity ratio is basically the ratio of the distance moved by the effort arm, or by the effort over the distance moved by the load. Is that okay? Is that okay? There are many conventions for velocity ratio, but as we consider many what's it called? As we consider many guys like that, many examples like that, many machines rather like that, we will see the different conventions for velocity ratio. Okay, so are you with me? Okay. So now there's also something called the efficiency of machine. This is another term we used to define machines. The efficiency of a machine is basically the ratio of this guy, the percentage of the ratio. Is that okay? Of its mechanical advantage over its velocity ratio times 100. Is that okay? The percentage of the ratio of mechanical advantage to velocity ratio. Now, I said it is the percentage of the ratio of mechanical advantage to velocity ratio. Does that make sense? Okay. And we said that there are two types of machine. Okay. We classify machine as ideal and real. Is that okay? So machines, all machines are real. Is that okay? There's no ideal machine. But in the ideal condition, efficiency of a machine is supposed to be equal to what? 100%. Is that okay? It's supposed to deliver 100%. But no machine in real life is actually 100% efficient. Is that okay? So the efficiency of a machine is always less than 100%. Okay. Okay. So what that means is that for an ideal machine, the ratio of the NA to the V, I hope you are listening now. For an ideal machine, the ratio of the mechanical advantage to the velocity ratio is always what? 1. Is it clear? Okay. All right. Now, what are the types of machine we have? Number one, we have the lever. We have the what?
lever,
Okay, let's consider the kind of machine we'll see. We'll talk about lever, pulleys, screw jack. Oh, it's pitch. The screw jack that uses pitch, old man. Incline planes, God bless you. inclined plane is a machine you don't know. Because how do we use ramps? It's when we want to carry a load. Okay, when we get there, I'm going to draw it. I'm going to show you how we use ramp. This is a lorry, right? We want to carry load inside it. Now put a ramp. I'm going to show you and why we do it. You see that it's actually a machine. Are we good? Okay. Have you written these formulas down? Because we're going to be using them almost all the time. Okay. The other formulas for mechanical advantage, you can also say it is work done by load over work done. No, work done on load. It's not by load. Work done on load over work done by effort. Is it clear? Okay. Let me put that down too. Work done on load over what? Work done by effort. Now, this is what confuses students about this work done by effort. Work done by effort is going to be the work done by effort is going to be the work done on load plus the work done to overcome friction. Do you understand? Work done used to overcome what? Friction. Work done to overcome. Work used to overcome friction. So that if you see a question that includes friction is particular Newton, so is, do you understand? You use that. Is it clear? Okay. And of course, in this case, you know what that means. Since work done is force times distance, what would that mean? What would that mean? This will mean what? Load times what? Load arm. Is that okay? What is the load arm? Distance moved by the load. Are you with me? Are you getting it at all? Okay. Then what would the work done by effort be? Force times distance again, right? That was effort times what? Effort arm. Are we good? That's distance moved by. For it to be work done, it has to be force times distance, right? Okay. Those are different conventions of the same formula. Are you with me? Okay, let's go to lever. Now, what is a lever? A lever is basically a type of machine that has the following parts. It has a load, it has a fulcrum, and it has an effort, and it has load. Not like it has load. We use efforts to carry load. Is that okay? And that thing has a pivot or a point, a fulcrum. Is that okay? On which two sides of the machine is resting. You understand now? Do you get it? That's what a lever is. So now we now have classes of lever. We have classes of lever. Okay? Now the first class lever. We have the first class lever, we have the second class lever, and the third class lever. There are three classes of lever. Is that okay? The first class of lever is going to be the one where, just use this mnemonic. Very simple. Very simple. Just use F, L, E. Here, E, F, L. Then here, L, E, F. Just fill it with what is not there. Is that okay? But the most important one is this middle. Most important one is what? Is this middle here. A first class lever is a lever in which the fulcrum is between the effort and the. A second class lever is the one in which the load is between the. While a third class lever is the one in which the what? Effort is between the fulcrum. Okay. What is fulcrum? Do you know? Let me draw something here. I'm going to see fulcrum now. What is this guy? What is this? Looks like it's scissors, right? Okay. You see the point, that hinge on which it is hanging on to cut whatever you are trying to cut. That's the fulcrum, the pivot, the point where it is hanging on. Is that okay? So now, let's check. In this This machine, you know, is a machine too, right? This machine is what type of lever? Let's see. Let's analyze together. Where will your effort be applied on? Here, right? So effort is here. Where is the hinge? Middle, fulcrum, right? Where is the load going to be? The paper you want to cut? Eh? So what class lever is this? First class, okay? How about this guy? What is this? Do you know what I'm trying to draw? Eh? Okay, good. How do you draw it again? Okay. So what class lever would this be? Eh? Let's see. Are you with me? So the load will be here. Your effort, your hand will be here. Good. Do you see that? Because the fulcrum is here, the load is here. The fulcrum is where it's hinging on, where it's resting on. You get what I'm saying? All right. How about this guy now? Oh no, I'm not drawing it well, right? Something like this. How do you do that thing? I don't know too. I'm trying to draw a hammer actually. It does look like a hammer, right? How do you draw that thing? Basically, the point is this. Now, when you want to remove nail, for example, you want to remove nail like this. Eh? You want to remove nail. This is going to hinge, rest on here, right? Isn't it? So this will become the what? Fulcrum, right? This will become the, God bless you, this will become what? So who is in the middle? Fulcrum is still in the middle now. Isn't it? Let's draw it upside down. So the load is to be, this guy is to be removed. So this guy is in between two teeth. So it's two teeth like this. This will not show. The other side will show like this. And we know it's gonna come like something like this. So this guy is resting on here. This is the load here. This is the fulcrum, right? This is the effort. Who is in the middle? Fulcrum. Do you see it? Is it clear? It's not clear. It's still first. If you think it's not first, raise your hand. If you are not sure it's first, raise your hand. Why? Which one do you think is in the middle? The fulcrum is in the middle, right? Which one do you think is in the middle? Fulcrum now. If it's fulcrum that is in the middle, it's always first. Is that clear? Okay, how about a tongue? This thing that we used to pick bones and puff off. You put puff off here. So what? Where do you hold? You hold here. So your effort is here. So your load is here. Your fulcrum is here. Now where is hinging on? So this is what? Third. God bless you. So it's what? Third. How about a plier? First. Uti. How about a biro? Biro will what? So if you know the answer to biro, drop it in the comment section below. No, don't think they will ask you in jam. They won't ask you down. But if you understand it well, you can analyze it. Simple. Huh? Some think it's first, some think it's second. I hope you know that a biro is called a ball pen. Why? Because there's a ball that is rolling from inside it. Do you know? You don't know. There's a ball that is rolling inside now. Inside this thing. This thing is a ball. You see it's separated from here. I don't know. Just analyze it. Okay. So that's for a lever. Is that okay? So for a lever, our velocity ratio is always what we did the other time, which is what? Distance moved by Distance moved by what? By effort. Distance of effort over what? Load distance. Okay. Now, how about an inclined plane? Let's look at analyze an inclined plane. We'll come back to this too. Now, an inclined plane. For an inclined plane, the velocity ratio, do you remember, is what? 1 over sine theta. God bless you. But basically, you know it's a machine too. Velocity ratio of inclined plane. VR for inclined planes. VR is what? 1 over sine theta. The reason is because it takes now look at this. Let me try to show you something. Although master the formula, nobody will ask you why. Is that okay? But it's simply because it takes, I'm coming. So you want to roll this load up this guy. So who will this be? Oh, this trolley. Give it to DMB. DMB is trying to roll this thing. So it's trying to overcome this load. Is that okay? Do you get it? All right. So the distance by the load is hypotenuse. Is that okay? And the distance that will be moved by the effort is this hypotenuse. But the load is moving this direction, this distance. Is that okay? So that is going to be over adjacent. No, over opposite. Consider this angle. We are considering this angle. Over opposite. Does that make sense? So, and that is inverse of sine. This angle here, the angle between the ramp and where we are doing the work on. Do you understand now? So, that's the reason why it is inverse of sine. Do you get me? Okay. So, that's VR for inclined plane. Then, how about for screw jacks now? For screw jacks, it's just that guy that changes the VR. So, let's get the VR. The VR for screw jacks is equal to 2 pi r over pitch. Is that okay? The reason for screw jack is what?
2 pi r
over pitch. Okay. What are we gear? There's also gear. Gear is also a machine. Is that okay? For gears, I think VR is equal to the driving over driven is equal to number. Okay, yes, I think I remember. Number of teeth of the driving gear over number of teeth of the driven gear. Is that okay?
Yes, sir.
Okay. And is equal to distance. Is it distance now? Moved by the formula is not here. But for the other guy, see, if it's number of teeth, just remember this. If it's number of teeth, it will be driving over driven. Then if it's for the other guy, I think distance, it will be driven over what? Driving. Okay. And you know what that means? You know gear now. So one gear is driving another gear. You understand? Do you understand? So this is the driven gear, this is the driving gear. This one is connected to the source exactly. Is that okay? So as this thing is moving this thing, this guy is driving, right? And as it's driving, this guy is being driven. Do you understand? Wake that big head. Right. Raise your head. Okay, since number 1 and number 2 are very simple, I'm going to be solving number 3 and 4. 3 is also very simple, but you know. So velocity ratio is given by 1 over sine theta. So velocity ratio, we got 1 over sine. What's our theta here? 30 granotes. So we have 30 granotes. So we got 1 over 0.5 or 1 over 2. So that becomes what? 2. Huh? That becomes 2. So number 4 now says a screw jack whose pitch is 2 millimeters. The pitch of the screw jack is what? Don't forget the formula of screw jack. The velocity ratio is what? 2 pi big R or any R over the pitch, right? This R is going to be the length of the jack. Is that okay? The length of the jack. Okay, there is also another thing. Wheel and axle. Wheel and ID. Is that okay? I didn't give you that. It's going to be big R over small r, or say velocity of this thing of wheel. Just it's going to be wheel over axle. Is that okay? Anything given for wheel over what? What's given for axle? If it's wheel and axle machines that you're giving, any machine that uses wheel and axle, is that okay? Okay, so for this guy, we know that VR is going to be that guy, so that will be 2 pi R over P. Okay, and P is VR, and P is given as the pitch, 2 millimeters. So since we calculate in centimeters, so we will convert this guy to centimeter. Are you with me? So how do we convert 2 millimeters to centimeters? Remember that 10 millimeters make 1 centimeter. So 2 millimeters will be how much? If 10 millimeters is equal to 1 centimeter cross multiply. Did you see what I did? Did you see what I did? So you say x equals 2 over 10. Does that make sense? So x will be equal to what? 0.2 centimeters. Are we clear on that? So it means that our VR will now be equal to 2 times pi times r. What is r? So our r is what? 40. Is that okay? R is the length of the jack. What do you mean by length of the jack? You've used the jack before, right? The pitch is the number of 1, 2, 3. Is that okay? Then this thing is the pitch and the length of the jack is how much up you're going and down. I don't know if you understand what that means. You get what I'm saying, right? Okay. So what did I even say? So this guy, right? So that will be times 40 over P, which is 0.2. Are we good? Here 1, 0.1. 400. 400 times 3.142. 125. 6.8. Okay. So we now say that if the jack has the efficiency of this, we should calculate the velocity ratio we have calculated at the mechanical advantage. Recall that efficiency is equal to what? MA over VR times 100 over 1. Or you simply say efficiency over 100 is equal to MA over VR. Does this make sense too? Just bring this guy down here. Now you cross multiply. It's the same. Basically, it's the same. But if you don't understand, just use this. Is it clear? These two formulas are the same. So efficiency is given as 60 over 100 is equal to MA. What is MA? That's what we're looking for, right? We've gotten VR to be 1256.8. So this now becomes here 60 times 1256.8 is equal to, what we say MA. MA is equal to 1256.8 times 60 all over 100. Is this clear? What's your MA? 0.08. No unit. What will now be the effort? Recall that effort is going to be what? Load over mechanical advantage. Mechanical advantage is effort, load over effort. So effort will now be equal to load over mechanical advantage. What's the load? Where is it? Okay, 900 kilograms. So we will now do it times 10. Answer J. That becomes 9,000 over, what's our MA? 754.08. So effort is going to what? 1. Effort is going to be in Newton. Are we good?
Work done by.
Then what will be the work done by the effort? Work done by the effort is going to be what? This effort times what? Distance moved by, are you there? Distance moved by effort, or we call it effort arm, right? Effort times effort arm. So what's the effort? 11.93 times. What's the distance moved by the effort? Through a height, yes, 20 centimeters. What does that give us? So that will be the answer. Let's go to the next thing. What's our next topic? Linear momentum and force. Okay, let's go. What's it? Given by small letter p. Momentum is given by small letter p and is given by is defined as the product of mass of a body and its velocity. Does that make sense? All right. Now, Newton's second law of motion says that the force applied is directly proportional to the what? Acceleration produced. So we know that we come up with the formula F equal to ma, and recall that a is equal to what? V minus u over t. This therefore means that F will be equal to what? M into bracket what? V minus u over t. This therefore means that now we have diverted from momentum to forces. Is that okay? I just wanted you to know where we are coming from and heading to. Okay, so we now have this as the value of force, or the representation of force, and we have that F times T will therefore be what? Mv minus mu. What is Mv minus mu? Change in momentum. So we see that m force times time, which is what? Impulse. Impulse is what? And this one is what? Change in momentum. Do you understand? So impulse is the same as what? Change in momentum. Tell anybody impulse is the same as change in momentum. All right. So now there is something with momentum. We tend to calculate what is called collision. So when they transfer momentum to each other, is that okay? When they transfer momentum to each other. So this is the way it is. When a body is moving in a direction and it hits another body that is along its path, it will transfer momentum to that body, or that next body will gather some amount of momentum if it wasn't moving at all initially. Do you understand? Okay, so we now have that. We now have initial momentum and final momentum. So we have collisions. There are two types of collisions, though. We have the elastic collision. Before we talk about the collision, let me reiterate what I said. I said that the first body, we have mass m1, and it's moving with a velocity u1. Is that okay? That at the end of the day, when they collide, that they are going to pass the momentum to the next body, and that next body is going to gain what? So if the body was stationary before, are you with me? The body is going to have u equals 0, right? So the body will not have any momentum. So it's going to be equal to so this will be the initial momentum before they collided. Initial momentum. So by the time they collide, the total momentum is always conserved. There's also what? Conservation of momentum, of linear momentum. There's also conservation. So the total momentum is always conserved. This amount of momentum at the initial start is going to be equal to the amount of momentum that they will gather at the end of the day. That will be m1 v1 plus m2 v2. However, this case is when this body is moving, if it's an inelastic collision. This one is for what?
Inelastic collision.
And the first body was not moving initially. Only one body was moving. So when that guy touches the other guy, let's say these two markers were moving like this. This one was rolling. Now this guy was not moving. But this guy is not moving. This one is not moving. And this guy is now rolling and rolling and rolling and hits this guy. Then both of them now begin to move. If it were elastic, they'll move at different. Usually, if it's elastic, they usually move away from each other. Is that okay? And they'll move at new velocities. But if the body was moving initially, if the two bodies were moving initially, now there are two conditions too. They could either be moving in the same direction or different directions. If they're moving in similar directions, it will be m1u1 plus m2u2. This is the case where the momentum of one is greater than the other, so that when they are moving in the same direction, they hit each other and might continue. Usually, they will continue to move in that direction. And if that is the case, then they will have m1v1 plus m2v2. If they move with the same, if the collision is inelastic and they begin to move together, then they have m1u1 plus m2u2 will equal to m1 plus m2, or let's do it this way: m1 will move with velocity v, m2 will move with the same velocity, so that it becomes m1 plus m2 into bracket v. They will have a common velocity. Does that make sense? This is the case where both of them are moving together with the same velocity and the collision is inelastic. Now that's the case. What if the collision here was elastic here? That's my point now. If the collision was elastic here, and especially when both of them, let's use billiard balls for example, and this ball is moving this direction, this ball is moving this direction. This guy is m1, this guy is m2. Is moving its initial velocity 1, velocity 2. By the time they collide, assuming that m1 was greater than m2, whichever one is greater, that's the one you arrange first. Is that okay? But assuming now that this guy is greater than this guy, this will be the initial momentum, the total initial momentum here will be m1u1 minus m2u2. Do you see the condition of minus now? Because they are moving what? Different. In opposite directions. Does that make sense? Now, consider the fact that if they move together, one of the forces will, one of the masses is greater than the other, right? So if they are moving like this, they separate for a while, then what will happen? They move in the same direction, because this one will lose its momentum, and then this guy will now, the new momentum that is together will now be the new momentum that they are using to move together. Does that make sense? Does that make sense? Yes, in that case, it's either if they move together, it will still come back to this m1 plus m2v. And if they move with different whatever, albeit the new velocity will be less. Is that okay now? Do we understand?
Yes, sir.
All right. We did not analyze kinetic energy throughout. Kinetic energy is the same. So for this case, what will be the kinetic energy? Is also conserved. Is that okay? Half m1u1 squared plus half m2u2 squared will equal to what? Half m1v1 squared plus half m2v2 squared. Does that make sense? Half is common here, so that will be half m1u1 Did you get this? Do you understand?
Yes, sir.
Now let's now talk about recoil velocity. Recoil velocity is under the same distance. Is that okay? The recoil velocity is this. This is what we mean by recoil velocity. You know, if you shoot a gun, how many of us have shot gun here? I always have people who have done bad things.
So it's toy gun.
Toy gun. Okay. So there was one time we were fighting one. Okay, let's continue. So this is recoil velocity. So if I shoot this gun, poof, and I shoot a bullet that day, what's it? Let me see it. I must say the truth. Look here. The guy experiences a jerk. When you shoot, you notice this guy will jerk, right?
Yes, sir.
It's because of recoil. It's, mommy, yes, ma. I didn't get to see my girl before she went yesterday. Okay, so I said that the recoil is because of the jerking of this guy. Is that okay? So what happened? Yeah, jerking. Yeah, you see a jerk to jerk. That's why you see people that shoot, except me. When Okay. Okay, let's go. Okay. Oh. Listen now. Did you not see when I wrote down the board? Alright, so the gun is going to have a particular momentum. Is that okay? So so this guy is called its recoil velocity. Is that okay? So the recoil, think of it as recoil momentum of the guy. Is going to be the momentum of movement or of that the bullet will use to go out. Is that okay? Do you understand me?
Yes. Yeah.
So this is the formula for recoil conditions. You have gone. Then that of jet propulsion, right, is the same. Is the same. The amount of energy that is dissipated here is going to be the amount of. Usually, you find velocity, the mass times velocity of the body. Let's find a question. You're going to see what I'm talking about. There are 3 questions here. Right.
That this everyone is it for elastic?
What do you think? If they collide here, this will be for elastic.
Okay.
This will be for elastic. That is, they hit and go with different velocities. Is that okay? Let's quickly go. Let's quickly go. A gun of mass 2 kg fires a bullet of. First, let me write the question.
Here we go.
We said mass of bullet of what? 15 grams, which is what? 0.015 kilograms. Yeah? Traveling at this. So the velocity of bullet, wait, it's going to be the initial, yeah? The initial velocity of bullet is going to be what? 300 meters per second. Strikes and is absorbed. So if it strikes and is absorbed, then this thing will be what? Will it be elastic or inelastic?
Yeah.
Inelastic. What do you see? And then the other codes then. Yes, sir. Use it. So, are we there now?
Yes, sir.
And it's absorbed, so it will enter. When it enters, they'll move together. Yeah. So, by a 70 kilogram object, so mass of object. So let's say mass of object times of O is 75 kg. So find the speed with which the object moves off. Okay, we weren't told if this body was stationary. So we'll take the assumption that it was stationary. So now that M1U1 will just be the sum of this guy's momentum of the bullet will be equal to, if they will move up together, right? M1 plus M2 V. Does this make sense? Is this clear? M1 is for MBUB. So that will be 0.015. See, the people that did not get it, they are the ones that are not concentrating. Don't worry. 300 is equal to M1 is what, please? MB now this time, and MO. Does this make sense? Okay. 0.015 plus MO 75 kg times V. So this by this 1 to 4.5 is equal to this plus this 75.015 divided by 75.015 75.015. So V equals what? So that's 0.06 meters per second. Very simple stuff. So you just complicate it. What did you say? Okay, so should we go to the next thing? Should I clean it? Switch it off. Or possible. Okay, so what's temperature? Okay, but I told you that thermodynamically, temperature actually refers to what? The total internal energy. Temperature is what?
Total internal energy.
So, but we perceive it as what? Hotness or coldness. And we told you the total internal energy is just what? Number of what? Kinetic energy or number of collisions, right? Total internal energy of a system. Okay? But it is perceived as heat. Perceived as heat. Okay? Now we have units of measuring temperature, and it's this conversion of unit that we basically want to address. And that's why we talk about temperature measurements. First, let's talk about the difference between temperature and kinetic energy. Now, temperature is, there is an instrument for measuring temperature, but there's no instrument for measuring units, energy, right? But they both have units here, but there's an instrument for one, there's an instrument for the other. And one is, what else again? Scalar and non-scalar. So when a body is stationary, so what proves that guy actually has an amount of energy is the temperature, right? Yes, because it is the degree of collisions. So it means that there can be I told you about absolute zero temperature, right? What is the absolute zero temperature? -273, right? It is -273 Kelvin that a body has 0 joules of energy. Do you understand? So that means in that condition, everybody in that guy is restive. None of the atoms are what? Moving or colliding. Is that okay? All right. So let's talk about the measurements now. The measurements, we have the units, degree Celsius, degree Fahrenheit. That's spelling again. And Kelvin, yeah? So on the Kelvin scale, let's have the centigrade scale. Centigrade or Celsius, right? Centigrade because it is cent, right? Degree Celsius, and of course whatever we're measuring here. Is that okay? Now for this guy, 180 difference, that's 212 and 32, right? Do you remember it? Okay. I mean, of course, if you want to do the conversion, that's what you can use. You don't have to master that formula we learned the last time. I've told you before, right? Then on the Kelvin scale, we have what? 373 Kelvin and what? 273 Kelvin. Okay. So what do you want us to convert from here to here now? No, if you wanted to, the easiest is from here to here, what do we do? Have to add what? 273. I want to convert from here to here, subtract 273. But if we want to go from here to here, let's merge the scales. So how do we merge the scales? Come here and say, let's say we wanted to convert 58 degrees Celsius to, am I on? Okay, 58 degrees Celsius to degree Fahrenheit. So just come here, draw the scale. You don't have to master the formula. Just draw the scale. Put the centigrade scale here. And the degree, the one you are measuring is what? 58, right? So 58 to be around here. 58 degrees Celsius. Does that make sense? Then the Fahrenheit scale, 212. Lower, yeah, there are two fixed points. I didn't mention that. They have the upper fixed point and the lower fixed point. And the difference between them is called what? Fundamental interval. Is that okay? Okay, so here, so we are looking for the degree Fahrenheit scale. Fahrenheit, what corresponds in degree Fahrenheit. So what you do is this: take the ratio of the lower fixed point and that point. That will be the ratio of the difference. Listen to me. The ratio of the difference between the lower fixed point and that point, and the lower fixed point and the upper fixed point. Does that make sense? So this means that we're taking 58 minus 0 over 100 minus 0. Is that okay? The ratio of this difference should be equal to the ratio of x minus 32 over 212 minus 32. Okay, this makes sense, right? This becomes 58 over 100 is equal to x minus 32 over 180. Now, by the time you cross multiply, you're going to have x minus 32 into bracket 100 is equal to what? 58 by this guy, what? 440. Okay, so what we now have is divide both sides by 100, so that we have x minus 32 is equal to 104.4. X will now be equal to what? 104.4 plus 32. So that x is equal to what? 136.4 Fahrenheit. So basically what we are doing is this. What the formula that we derive, I can't even remember now, but I remember that the formula that we use for it is just that 58 that we want to convert. No, that x, let's generate an expression for x. X will be equal to 180 times 58, calm down, over plus 32 at the end of the day, right? Plus 32 over what? 100, right? This takes care of this takes care of this. Or say 2 year 5, 2 year 9. Okay, so the formula therefore becomes what? 9 times degree Celsius scale, guy. Does this make sense to us? All over 5, all plus 32. Is that okay? That's from degree Fahrenheit to degree Celsius. Oh, thank you. Degree Celsius to degrees Fahrenheit. Do we understand? And of course, if you make degree Celsius sort of formula that you get, should we make it? If you like, you can cram this, but I mean, I just, So just say 9c over 5 plus 32. This is not 9c plus 32. Everything here plus 32. So at this place, we now have that degree 5 degree Fahrenheit will equal to 9 degrees Celsius plus 32. And we're looking for this guy, right? So that will be 5 degree F minus 32 all over 9 is equal to degree Celsius. There's a way to work this out. No. C over 5. I can't hear you.
C over 5 equals to F.
C over 5 equal to F. Everything over 9. For this guy. Because I see that this guy is supposed to open the bracket. If this guy came here first in mathematics, this is supposed to come here before we could multiply. Is that okay? I forgot that. So it's the same. Do you see? It's the same. It's the same. Like C is equal to 5 into bracket F minus 32 over 9. Does that make sense? All right. So that's that on conversions. Now we have types of this guy, thermometers. The instrument used for measuring temperature is what? Thermometer. And we have different types of thermometer. What are the types of thermometer? Yes, we talked about those liquids that are used in thermometric liquids, right? They are what are called mercury. Why is mercury preferred over alcohol? It does not wet glass. And then God bless you, high melting point, good conductor of it, God bless you. Of course, because it's a metal, right? That's a good conductor of it. All right, let's go. So we're done with that. It's just conversion. Most of the questions about conversion. Okay, you could now see something like this. For example, the one that is the constant volume gas thermometer. You'll be giving your volumes. Is that okay? You'll be giving your volumes. Upper fixed point will be volume 1, lower fixed point volume 0 or volume 0. Do you get it? And you'll be told to find the particular distance. Just use the same idea. Should I solve one question?
Yeah.
Okay. First, please let me write this question. This one is about resistance. Let's go again. The resistance of a platinum is this at the temperature of steam. The temperature of steam is what? 100 degrees Celsius, right? Upper fixed point. So we have this. At upper fixed point, the resistance is what? 5.684 ohms. Then the lower fixed point, it says at 760 millimeter mercury, and this guy at what?
5.2.
5 point at 0 degrees Celsius. Is that okay? This is 100, that's 0. So this is 5.684 ohms. 6, okay, 5.240 ohms, okay? At terms of, so in other, if the resistance at the whatever of warm water is this, so you now come here and say X. Are you with me? 5.490 ohms. Is that okay? Like we are using a particular scale resistance wire. You understand? You know it heats up, right? So, and do you remember when we were doing resistance, we talked about the fact that the resistance, the heating, as the heat increases, what happens to resistance too? It increases, right? Heat increases the resistance of the wire. So that's why they can relate temperature and the resistance of the wire here. Is that okay? So it now says calculate the liquid temperature. So what will be the temperature of the liquid? That's just it. Do you see the way I set it up? Okay. So then the idea is simple. These two upper and lower fixed points, or you start from here, x minus 0, the ratio with 100 minus 0 should be equal to this minus this, 5.490 minus 5.240 over 5.684 minus 5.240. So x over 100 is equal to what? This minus this is what? Over this minus this is what? 0.444. So when you cross multiply, x will be equal to 25 over 0.444. X will be equal to what? Ohms. Does that make sense? Okay, degrees Celsius, sorry. And that makes sense, right? That makes sense. Okay, so that's the setup for that. Now let's go to expansivity. Are you with me?
Yes, sir.
How is that sharp? I like it. I like it. Expansivity. What is expansivity? Basically, response to heat, right? Okay, increase in any of the quantities of that solid, right? If it's in its stretch, not the stretch now, but I call it, if it's linearly, if it's in its length rather, what will we call it? Linear expansivity. If it's in its area, yes, and if it's in its volume, cubic expansivity. Now there's also a phenomenon known as apparent cubic expansivity, but let's just quickly go by. For linear expansivity, we denote it by alpha. Alpha is just saying first expansivity, is that okay? The first type of expansivity is in the linear so which is, we said linear expansivity is the change in length per unit rise in the temperature of the body. Does that make sense? Then area expansivity, that's second expansivity, could be in the area. It's going to be what? The change in area over A naught. I know, and you know that, or A1, it could be A1, whichever convention you're using in your textbook, change in temperature. Does that make sense? So this one is going to be L2 minus L1 or L1 minus L0, whichever convention you use, over L1 bracket theta 2 minus theta 1. This makes sense, right?
Yes, sir.
This one is going to be area 2 minus area 1 over theta 2 minus theta 1. And if you are given in degrees Celsius, you don't have to convert here, because if you convert to Kelvin, albeit our unit is in Kelvin. Do you remember? Our unit is in Kelvin. But you don't need to convert still. What's the unit of linear expansivity? Length cancels length. That's what? Per Kelvin. That's what? Per Kelvin. And it is discovered that the relationship between this guy and this guy is what? Area expansivity is what? 2 times linear expansivity. So then this guy, 3 alpha, right? But what's the formula? Change in volume over V1 into bracket theta 2 minus theta 1. Okay, so let's attempt. Okay, then there is apparent cubic expansivity. It's defined as, right, apparent cubic expansivity is defined as the increase in volume per unit temperature rise. Oh, it's the same thing, only that it can use mass of liquid expelled, because listen, do you remember mass of water and its volume? We can interchange them, use them for each other, right? Why? Because water at 1 kilogram of water will contain exactly what? 1000 cm 1000 cm cube of water, right? Okay, which is 1 meter cube. Okay, so that's what this idea is about. That is the mass, apparent cubic expansivity, is y sub a, okay, is equal to mass of liquid. Write it down. Right, of liquid expelled over mass of liquid remaining times temperature rise. Liquid expelled over mass of liquid remaining times change in temperature. Okay, so I'm not solving any question in this one. I was just giving you the question. Is that okay? Because it's very what? Simple, good. Okay, solve this question. Steel bars. What we are doing is we are calculating, what we are looking for is basically change in volume, not volume 1 or volume 2. Does that make sense? So the change in temperature also is what? 40 degrees Celsius, because it's from 0 to 40, right? Then linear expansivity is what we're given. Is 1.2 by 10 to the minus 5 per degree Celsius. So volume of expansivity will now be what? 3 times 1.2, yeah? And so it's by minus 5. Do you know what I did? Okay, because that's the relationship between linear expansivity and volume expansivity for the same material. Is that okay? For the same material. So for example, if this were steel, now we're talking about that of steel. So what? This times is 3.6 here, times 10 to the power. Am I wrong? No. So we now have that this guy is going to change in volume over initial volume minus times change in temperature, right? So changing this guy is 3.6. That will be 3.6. Are you with me?
Yes, sir.
Times 10 to the power minus 5 is equal to the change in volume. Take note, we are looking for, calculate the increase in volume. It's the change in volume that we're looking for. Just trying to emphasize. So V1 is what? When the volume of this guy, does that make sense? That's the initial volume, 1,500 or 15,000, 1,500 times the change in temperature, 40. Does that make sense? So what becomes of this guy? We have change in V is going to be 3.6 times 1, 2, cancels the, let's just do it, right? Minus 5 times 1,500 times 40. Are you with me? These guys take care of 5, remain 1, right? Or 2 rather, right? 2, right? This by this, 60, right? Remains 1, right? Then 6 times this is going to what? 126, right? 126 times 10 to the power minus 1. That's 3.6, that will be 12.6. That will be 0.1.26. So the answer is 1.26. times, no, then times 216 rather, not 126, right?
Yes, sir.
216. So that will be 2.16. That's 2.16 centimeters cube. Does this make sense?
Yes, sir.
Okay. So from here, we have written this formula. I've written this formula.
Yes, sir.
Okay. So number 2 says that the length of a side of a metallic cube is this guy, at this guy is that guy. So the length, L1, let's make it L1, is 5 centimeters. So we will convert to meters. Is that okay? Let's convert it to meters. Yeah? Is in centimeters? Okay, we don't need to convert them. Eh? Number 2. I don't know, let's verify it. 0.02. What did you say? To meters. Convert this guy to centimeter cube. Calm down. He said the length of a metallic, the length of a side of a metallic cube. Okay, cube. That makes sense. So volume of cube is what? L cube. That becomes 5 times 5 times 5. That'll be 5. That'll be 125 centimeters cube. But if you want to do it in meters cube, that becomes what? Divide by what? 1000, right? Or you say 0.05 times 0.05 times 0.05. Does this make sense? Huh? In meters or in meters? What's the answer given in? It might be given in meters, so let's convert to meters. Is that okay? Well, convert this guy will not be divided by 1000. It will be divided by what? Which 100? Simply say 1 centimeter, 100 centimeters gives us 1 meter, right? So 100 centimeters times 100 centimeters times 100 centimeters is equal to 1 meter times 1 meter times 1 meter. Do you know what I just did? So this is what? 1 million is divided by 1 million. Because we are saying that I'm saying 6 dp. Centimeters cube now. You know this conversion factor, right? If you don't understand it, raise your hand. If you don't understand, raise your hand. You don't understand it. Can you convert from cm cube to meter cube first? And that's what do you do? You want to convert from centimeter cube to meter cube. Calm down. See, it's simple. It's simple. What you just do is divide by 1 million next time. Is that okay? But if that doesn't make sense to you, what I did is just, you know that 100 centimeter makes 1 meter. That's why I tried to simplify it. 100 centimeter make 1 meter. So 100 centimeter times 100 centimeter times 100 centimeter will give you 1 meter. This one is 1 meter, right? Times 1 meter times 1 meter. That is what? 1 meter cube. Does that make sense? So 1 million centimeters cube is equal to what? 1 meter cube. Therefore, 125 cm cube equal to x. Do not cross multiply. Does that make sense? So which means you're dividing by 1 million. Is that okay? All right, but I have to know the factor because it's becoming too big. But anyways, 125 over 1 million over what? 123. 1.25 times 10 by what? Minus 4. Good. Because we returned by 1. So that will be minus 1 minus 4. So that will be meters cube. Are we good? So this is the volume. It now says that we should find the volume of the cube at this. So that will be V2. Does that make sense to you? That will be V2. That will be V2. And the linear expansivity is this, right? So if alpha is 4 by 10 to the minus 5 per Kelvin, then gamma will be equal to what? 3 by this, that what? 12, which will be 1.2 times 10 to the power what? Minus 4. Does that make sense? Okay, per Kelvin. Okay, so we now have that gamma. This gamma This gamma, should I clean this? Yes. Okay, degree change in temperature is what? From 120 from 20 to 120. That will be change in temperature is what? 100, good. So delta theta is 120 degrees Celsius minus 20 degrees. And you can arrange it arbitrarily, as in, not arbitrarily, as in what I mean is, put the big one first and put this up. Do you understand now? All right. So now say that this guy is equal to change in V, which is what we're looking now. We're looking for V1 minus V2, right? And let's get the change in V first. That makes sense. Over V1 changing times 100. Does this make sense? We got V1 to what? This guy. So our gamma, which is 1.2 times 10 to the power minus 4. Are you with me?
Yes, sir.
Everything is playing. Is equal to change in volume over V1, which is 1.25 times 10 to the power minus 4 times 100. Okay, let's reduce it. That'll be minus 2, right? Does this make sense? Okay, minus 2. So that delta V will be equal to what? 1.2 times 1.2. 1.2 times 1.25. Let's do that. 1.5 times 10 to the power minus 4 minus 4 minus 4 minus 2, that's what? Minus 6. This is delta V, right? And delta V is V2 minus V1, right? So we now have that if delta V is this, that's 1.5 is equal, times 10 to the power minus 6 is equal to, what is V2? That's what we're looking for. Minus what is V1? 1.25 times 10 to the power minus 4. This is where mathematics will not scatter some people's head. And it's very, I've told you how to do this kind of thing. Just bring them to the same power of 10. Is that okay? So see what we're trying to do here. We're trying to do 1.5. So V2 from here will be equal to what? This one plus, does that make sense? So that'll be 1.5 by 10 to the minus 6 plus 1.25 by 10 to the minus 4. See what I'll do here. Is it that I reduce this guy to minus 4? No, increase. That will be increase, right? Is that I increase this guy to minus 4? I reduce this guy to minus 6. Does that make sense? So which one should we do? Let's increase this guy, right? So how do... Are we fair? Okay. If we wanted to increase this guy, what would it become? To become V2 because what? We want to increase it. It becomes what? We'll bring now, what I'll do? I'm going to move, I want to reduce this guy by 2 places. You understand? I want to reduce it by 2 places. So if I'm reducing, now will I move forward or move backward? If I move forward, no, I'll move backwards. If I move forward, this thing will increase. You get it? Because this value will become bigger. Does that make sense? All right. You can use your calculator if you don't know it. So, anyways, but because jam, your calculator, I don't know. Well, okay, so what you do is you move it first time, right? This one reduced by 1. Move it the second time. Does that make sense? So your point is now, you now have points, fill this place with 0, 1, 5. Times 10 to the power minus 4. So you put 0 here. Does that make sense? Plus 1.24 times 10 to the power minus 4. So you can now add without fear now. Now say this guy plus this guy. That will be 1.24 plus 0.015. What does this become? This becomes 1.245. So that becomes 1.255, thank you. 1.255 times 10 to the power minus 4. Is that clear? Is it hard? Is it simple? It's very simple, right? So should I ask number 3 or not? No. What's the time? Okay, we still have time. How many more topics have we?
5.
3.
Two.
That's two. Yeah.
No, it's like three. Not so many. I meant of it.
Ah! No. Did this switch off by itself? All right, this will be a wrap up of the class because the mic switched off due to some I don't know whether it's witchcraft and but God forbid, because we prayed before we started. Anyways, every evil over your exam is cancelled in the name of Jesus. Anyways, I'm gonna link the video in the description where we have fully covered heat gain and weight loss. I'm sure it's this part that thing started because there had been. Anyways, do want to subscribe to the channel and share the video with your friends and subscribe. God bless you.